Hello friends. Today we're going to be discussing about the Dijkstra's algorithm in graphs. So, what is the use case of Dijkstra's algorithm? Like, what it is used for? So, basically, when you talk about Dijkstra's, it is basically used to find the distances of a source node to all other nodes of a graph. Like, what are the minimum distances by which we can reach to all of the nodes of a graph from a source node? Dijkstra's algorithm is useful for finding those distances. Like as the sequence also says that it is used to find the shortest distances of a node from all the rest of the nodes of that graph. Suppose we want to find the shortest distances. Let's take example of this graph. So we want to find the shortest distances by which from 0 I can reach to all other nodes. That is 1, 2, and 3. What are the minimum distances that has to be covered to reach all these 3 nodes individually? Okay, so if I want to go from 0 to 1, I see that 0 to 1, the shortest distance is 5. So I think it is for 0, it is for 1, it is 5. And from 0 to 2, if I want to go from 0 to 2, then it's 8, because this is the only possible. Okay, but what if I want to go to 3? There can be multiple ways, right? There can be one way which we can follow is this one, and which will ultimately result in a distance of 7. And there is another way by which we can go and reach to 3, and that is this one. But Dijkstra's algorithm basically gives us the minimum, and that's something what it is used for. It is used for finding the minimum distances by which we can reach from source to other vertices. So here it is 7, and here it comes out to be 14. So what we want is the minimum one. So 7 is going to be the minimum distance. So it will give us that distance. It will avoid this one, and it will give us this distance. That is something Dijkstra's algorithm is used for basically. So what are the steps? First of all, let me clarify that where can Dijkstra's be used and where it can't be used. First and foremost, Dijkstra's can only be used in weighted graphs. Obviously, you want some value for these edges only, then you can compare which one is minimum and which one is not. So you want the graph to be weighted, obviously. And second one is that it can't be implemented in graphs which have a negative cycle. I'll talk about that later, but first of all, let's try to figure out what are the steps to find out the minimum distances from a source node to all other nodes of a graph using Dijkstra's algorithm. So starting off, let's take the example of this graph only. Like I have told you that minimum distance is from 0 to the rest of the nodes. So it is for 0, it is 0, because obviously if you are starting from source node, the amount of distance that it will take to reach the source node is 0, because you are already present in the node, so the distance is going to be 0. But when it comes to other nodes like 1, it is going to be 5, for 2 it is 8, for 3 it is 3, for 3 it is going to be 7. We saw how it was calculated. So coming on to the step, how will you be doing this? So first of all, we will be initializing a distance vector where the distances, which will be a distance vector, which will basically be storing the distances that we are requiring, like the distances, the minimum distances. Okay, and initially all of these values will be initialized by infinity, except the source node, because you have an idea of what the source node distance is going to be from source node, that is 0. So we will see the distance of 0 is 0. 0 is basically our source node. It can be any other node as well, but for this example, we are taking the source node as 0. So we will mark that distance of 0 as 0. Okay, and the rest will be infinite. So moving on to the next step now. Now, at the second step, or we can say the third step basically, because on the second step we basically initialize the distance of the source node to 0, which is a step in itself. So, and the third step, we will require the need of a data structure. a data structure which will help us in finding out the optimal way of moving forward to other nodes with the help of the results which we have already find out. But that stage, I think it's very difficult to understand that in steps. So I think I will hard code one example for you to explain it to you in a better way. But for now, let's just take a glimpse at what steps are going to be like. Then I'll hard code example for you to explain as well. Okay then. So distance comma node. So initially we had like this pair 0 comma source. So this data structure will basically be storing pair values, where the first value will be representing the distance and the second value will be representing a node. What will this distance be? This distance will basically be the distance that so far is found out to be the minimum to reach to node from the source. What did I say? This distance is nothing but the so far discovered minimum distance from source to node. This pair is going to be put into this data structure. Okay, so initially we had just this. So initially we will put this 0 comma source into our data structure. So 0 comma 0 is being put. On the next step, what will we do? On the next step, we will start copying out the values. Like because 0 here, because 0 comma 0 was the only pair that was possible, that was present in the data structure, so we pop out. We basically pop out. So now what we want to do? We have our node and a distance. So we will be traversing, but it's not node comma distance. It is distance comma. I've already mentioned it here. Okay. So we will be trying to go into the neighbors of 0. So what are the neighbors of 0? According to the adjacent list that we have found out. And the neighbors of 0 are 1 and 2. And so 1 and 2. So far, the amount of distance that it took for us to reach from source to 0 is 0. And if you want to go to 2, if you want to go to 1, then we further have to travel a distance of 5. So 0 plus 5 is going to be 5. Now, now we have a better option here. 5 is lesser than infinity because the distance, what is distance basically storing? The storing the distance is, the minimum distance is y, which we can reach from source to that particular node. The value of distance I, the value of distance as is what? The minimum distance from source to node. Okay, so 0 plus 1 is 0 plus 5 is equal to 5, and which is obviously better than infinity, so we should be updating it, right? What just common sense says that if you have a better option, you should be updating it. So we will update the value by 5. Okay. And because we are updating the value of 5, we will put that into our stack. The distance was 5 and the node we reached to was 1. Okay. And similarly for this one as well, from 0 to 2, if you want to go from 0 to 2, we have to travel a distance of 0 plus 8, that is 8, which is obviously lesser than infinity. So what does common sense says that if you have a better option, you should be updating the values. You should be updating the values for, so we must say that because 8 is much lesser than infinity, we should be updating it. So the distances that we have found out so far to reach from source to 1 is 5 and from source to 2 is 8. Okay, because we have updated the distance of 2 as well, so we're gonna be inserting the corresponding pair of distance from our node into our data structure. So we popped out this one, and the new nodes or the new pairs that I introduced into our set are basically 1, 5, 1 and 8, 2. Now you might be getting an idea of how will this be done, but let me just complete the steps once for you. And now this data structure is not going to be a normal queue or stack, but indeed is going to be a data structure which will always return as the pair with the minimum distance. With the minimum distance, like here we have two pairs, present in our data structure, that is 5, 1 and 8, 2. But we want the minimum one because what we are trying to find. We are basically trying to find the minimum distances, like you reached from point A to point B. Okay, now you have reached to point B in the most optimal one. Okay, and you further want to reach to C, D, E. Okay, so what does common sense says? That if you have reached to this point in minimum distances, and you obviously want to prefer to go from this way only rather than going from another way which was having like more distance, more distance. If y is lesser than x, then obviously you should be willing to go to these nodes with the help of this one, this path rather than this path. This is what we are trying to say. We will basically be finding the pair with the minimum distance from this sec, and which data structures can be used to do it. Like we want to perform it in the most optimal way. So the data structure that comes into on my mind basically is either a set or a priority zone. So you can use any of these two data structure, but for this particular explanation, I will be using a set. You can do the same with priority zone as well. It is not much of a difference. It will give you the same result. Now, basically, we are concerned about the data structure, not what kind of data structure are we using. So basically, we will be getting the minimum distance out. So this process, these steps will be repeating again and again as long as this data structure will not become empty. Now explaining in this way can become a bit typical. So let me take an example to hard code and explain how is this going to work. So stay tuned. So here is the example. This is our graph and this is our source node. We want to reach from one to all of the nodes. So as per the steps, what is the first step? First step is basically to initialize a distance vector, which will be storing the minimum distances from our source to all of the nodes. So it is going to be like infinite, 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 infinite. How many nodes are there? 1, 2, 3, 4, 5, 6. So yeah, 6 hint. So this is node 1, this is for node 2, this is for node 3, this is for node 5, this is for node 6, and this is for node 6. Okay, initially all of these values are going to be initialized with infinite. But because we know that we're going to be starting from source node 0, so there is no meaning of keeping this infinite, so we'll be doing it 0. Okay, now, what was the next step? The next step was to maintain a data structure set or a priority queue, which will help us in finding the most optimal way to move to further nodes. So initially, what was the plan? The plan was to put the source node, that is 0, 1 here into our data structure. So we put it. Now what is the next step? The next step was to pop out the pair with the minimum distance. And because here the only pair that is available in this set is 0, 1, so the only option that we will be getting is 0, 1, where 0 is the distance and 1 is our node. So we want to travel into the neighbors. Now for 1 we can only reach to 2, so with a distance of 1. So we reached it to 1 by a distance of 0, and if you want to move to 2, we further have to travel a distance of 1. So our overall distance to reach to 2 is going to be 1, which is obviously better than infinite, so we should be updating it. And because we updated it, we also have to put that pair into our stack. So the distance was 1, and the node was 2. So we put it. Now on the next iteration, we will pop out this particular pair, that is 1, 2. From 2, we can reach to 3, and we can reach to 4. And for reaching to 3, we can have to cover a distance of 5, and for reaching to 4, we have to cover a distance of 3. And to reach to node 2, it took us 1. So if you want to reach to 3, the distance that is going to be covered is 6, which is obviously lesser than the already present one, that is infinite. So we must be updating it. So it is updated. And because it is updated, we must also be putting it into our set at the same time. So 6, 3 is put into our set. Now, for reaching to 4, we have to travel a distance of 3. So 1 plus 3 is 4, and 4 is obviously lesser than infinity, so we must be updating it. And because we have updated it, we must be putting that into our set. Okay, so far so good. Because we worked out, so we must be cancelling it out. Okay, now because this is a set, this will return us the minimum distance pair, which is nothing but 4,4. So 4,4 is formed now. Now we want to go into the pairs of, and we want to go to the neighbors of 4, which are nothing but 3 and 5 and 2. Okay, for the distance is 3, the distance is 4, the distance is 1, and for reaching up to 4, the distance has been nothing but 4. So if you want to go from 4 to 3, the distance is going to be 4. So is it lesser than is it lesser than the already present? The distance is going to be, it's 4 but 5. 4 plus 1, 5. Okay, which is lesser than the already present distance of 3. So I think we have a better way. So we should be updating it. Okay, it also makes sense that if you want to go from, if you go from this way, the distance is 6. But if you go travel from this way to this way, it is like 1 plus 3 plus 5, that is 6. But 1 plus 3 plus 1, that is 5. So Dijkstra is working, and we are finding the optimal one, and we are getting the optimal one. And because we have updated it, we must be putting this into our stack. But wait for a while. There's one more concept to understand here, that because we have updated a previously updated value, I think we must be looking for this one first into our set, because this is of no sense when this is updated to 5, right? What is the significance of having this in our set when we are already having a minimum distance to reach to 3, which is better than this particular one? So what we will be doing is, in such cases where we are updating our already updated value, and that previously updated value is present in our set, we will be trying to remove it first. Okay, we will be trying to remove it first to optimize our code, and then we will be trying to push that into our set. So now the newly updated value is 5, so we will be putting that into our set, that is 5, 3. So keep this in mind, we will be coding it as well, this particular portion, so bear with me. So our set looks like something like this. So if you, okay, so moving on, if you want to reach to 5 from 4, so 4 plus 4 is 8, which is lesser than infinity, so update it. Okay, we update it. Okay, if you want to reach to 2 from 4, the distance is going to be 7. So is it lesser than the already present one? I don't think so. So we will not update it. We update it in this way, we update it in this way, but we don't update in this one because we already have a better option, that is my distances. We already have a better distance in place of node for reaching to node 2. So we won't update. Now, our set looks something like this. We popped that 4,4, so then we can see it out. Now our set looks something like this. Okay, so 5,3. 5,3 is going to be worked out. Now where can we reach from 5? Like I can reach to 3, I can reach to 4, and I can reach to 6. For it is going to be like distance 6, it is going to be 4, it is going to be 3. And to reach to 5, we require a distance of 8. Yeah, we require a distance of 8. Now if you want to reach to 3 from 5, the distance is going to be 14, which is not a better option because we already have a better one, that is 5. So we want to give any emphasis to this value. Now if you want to reach to 4 from 5, the value is going to be 12, which is greater than the already present, so give no significance to it. But if you want to reach from 5 to 6, the value is going to be 11, which is lesser than infinity. So we must be replacing it, we must be updating it from infinity to 11, and this is how it will be done. So we formed out 5,3, and the last, and because we updated this, so we must put it to our set. So 11, 6 is being put into our set. So 11,6 will be popped out in the next iteration. And where can I go from 6? The only place where I can go is 5. And that is with distance 3. And the amount of distance it took for us to reach to 6 from source node is 11. So if I further travel down to 5, it will require a distance of 14, which is not better at all than the already present 8. So we really no emphasis to this one. And our set will become empty. And our algorithm will end at this place. And in distances vector, if we look at the distances vector, it will basically be covering all the minimum distances that will be required for us to reach from source to all individually. This is for node 1, this is for node 2, this is for node 3, this is for node 5, this is for node 6, and this is for node 11. You can check out in this graph by yourself. These are the only distances. These are vertical distances only. So let's try to code this down. I hope you would understand this. Try to hard code it on your own for better understanding, because algorithms like these require a bit of understanding and time. So you must be dedicating some time by your own, like hardcore examples like this, to understand it better. So now let's code it down. So here is our code. So basically let's try to go down. So initially what we did is we tried to initialize a distance vector where each value was initially assigned infinity, a value of max, that is infinity. And what we did is, because we know that the distance of source from source is going to be 0, so we did this. Then what we did, we initialized a data structure set, in our case, to hold those pairs of distance and nodes as mentioned earlier. And initially we put this particular pair. Okay, so then we'll go and run a while loop as long as the stack is our set is not empty. So I'm putting unlike, and here we are basically trying to find the pair with the minimum distance. So initially it will be this only, but only. So then what we will be trying is we will get this out and we'll be deleting it. Okay, the distance will be represented by the first value and the node will be represented by the second value. Then what we do? We traverse in the neighbors of our node. Okay. And in the distances of our neighbor node, like distances was what? The distance was basically the value for that neighbor node in the distance is greater than distance plus neighbor distance. And what we must be doing? We must be updating it. Okay, like the way I did above. And whenever I would find a distance lesser than the already present value in the distances vector, I would update it, and that is something what we are doing here. If the distances on the neighbor node comes out to be greater than what we can have, then we should be updating it, right? And we must also be putting that pair into our set. And why is this here? And I told you that there was an instance where we had 6,3 into our set, and then came another pair 5,3. So what was the significance of this if I have a better value of 5,3? So this particular portion of code is to remove this one. If we have this value, then we must not have any significance, because we already have a better option available, that is 5,3. So we must be removing it from the set, and that is something this part is here for. Okay, so I hope you could understand this. Try to hardcode the above example on your own, you will understand it. Okay, what is going to be a time complexity for this code? So basically, if you see, we are what is the insertion operation of a set takes? It takes log(n), and at max, what will we be doing? Suppose they have a graph like this, 4, 5, 7, 10. Okay, where every node is connected to every other node. Then initially, let's say source was 1. Then 1 comma 0 will be updating all the distances, and these all pairs, their corresponding pairs will be put into this state. So what we can say is it can be like the number of edges log into logarithm. And number of edges and log v is basically going to be a time complexity overall. Like you can either unit it on your own, but the post complexity is obviously going to be like if you don't consider the edges and distress, obviously you don't work to consider it. Then this going to be like most like next, yeah, you're in a space of v, that is the number of vertices. So the space complexity is like this, and the time complexity is e log v, where e is the number of edges and v is the vertices. So this was from my side about Dijkstra's. I hope you could understand the concept. I tried my best to make you understand. I know it was really fast, but I wanted to keep this video very concise and just straightforward. That's why I tried to take it a bit faster. So thank you for your time. Thank you for testing on your release. And looking forward to have you in the next video as well. Till then, stay healthy, stay happy. Bye bye. See you in the next video. Thanks for your time.